Okay, so last class we talked a little bit about basic probability and how it works. And we talked about the three types of probability. The subjective, which is just the educated guess, and really the mathematics behind that is kind of, well, a little bit vague, and what math there is complicated enough that we're going to just stay out of that for this class. There is theoretical, which with theoretical probability, it usually deals with number of successful results compared to total number of results. But that one implies that everything must be equally likely. Like rolling a die. Each side of the die has the same chance, equally likely chance of coming up. And then we have our experiential, or it's called empirical is really the name for it. An empirical probability is that relative frequency. And we did that yesterday off of a frequency table that we converted into a relative frequency table. Now we could have data that's given to us as a relative frequency table. For example, let's say that we are given that, let's look at number of children per household. And then let's say 0, 1, 2, 3, and 4. And let's say nobody in our survey or in our group had more than 4 kids in their household. And okay, let me take a, here we go. Okay, so let's look at a relative frequency now that is given. And I'm just going to throw these up there. Now, remember, the qualifications for these relative frequencies, for any probability, is that probability must be between 0 and 1, and the total for all of them must equal 1. They must add up to 1 total. So as I throw in these relative frequencies, just like relative frequencies all must add up to 1 as well, same with our probability. So if I throw in some numbers here, let's just say that there's the relative frequency of households with no children is 0.18. With 1 child is 0.31, so 49. 2 children is 0.32. 3 children is 0.17, and 4 children is what do we got there? I believe 0.02 is what we have to make that add up. To double check, let's just go ahead and add those. We've got 49, 81, 98, yep. That is 1.00 is what that adds up to. So that is a valid probability distribution. And now we could be asked, what is the probability that a randomly selected family has at least 2 kids? Now there are 2 ways we can approach this. The first way we can approach it is just say, here's 2, at least 2 is 2, 3, or 4, so we can add those up. 0.32 plus 0.17 plus 0.02 is going to give us, what, 0.51? That's the probability. The other way we could have approached that, in this case it wouldn't be a whole lot of help, is we can know that this whole distribution has to add up to 1, so I can take 1 and subtract out the pieces that are missing. Subtract out the 0.18 and the 0.31, and I still come out with 0.51. Now in this case, okay, I could add together 3 numbers, or I can take 1 and subtract 2 numbers. It's about the same amount of work. But let's look at an example where it might be a little different. And actually first I'm going to show you an example here that looks close to this, but not quite. What's the probability that a random selected family have greater than 2 kids? Greater than, or they could have said more than, would have also worked. In either case, 2 is not included. So what we'll be looking at here is 3 or 4, not the 2, 3, or 4. because 2 is not greater than 2. 2 is not more than 2. So that would only be the 0.17 and the 0.02. Here was 0.19 is the probability that a randomly selected family had more than 2 kids. So what's the probability that a randomly selected family had at least 1 kid? So this is now saying at least 1, which would be 1, 2, 3, or 4. I can add up those probabilities. 0.31 plus 0.32 plus 0.17 plus 0.02. And it's going to add up to 0.82. Or in this case, it would have been easier to say, hey, the whole thing adds up to 1. This includes everything but 0. So I'm just going to take 1 and subtract that 0.18. Get 0.82. So you can use that fact that it adds up to 1 total. Now the other thing I wanted to emphasize here, I know I'd mentioned it on Wednesday, but it bears emphasis here. The big difference here between at least 2 and greater than or more than 2. And on the other side, it'd be the same way of probability of having no more than 2 kids. That's including 0, 1, and 2. Or the probability of having 2 or less. That's also 0, 1, or 2. Compared to the probability of having less than 2 kids. Well, less than 2 kids would just be 0 and 1 because 2 is not less than 2. Or the probability of having fewer than 2 kids. Again, 2 is not included in that because 2 is not fewer than. So something to be careful of. Okay, so let's get off the review and get into the new material here a little bit. Let's take a peek at the marbles again that we talked about. We had 20 marbles in a box. And let's say that 12 are red and 8 blue. And just like Wednesday, let's say that all the marbles have the same texture, same size, same weight. They're indistinguishable except for color. So if you can't see, there's no way you can, by feel, that you can tell the difference between them. So we reach into the box and randomly draw out a marble. What is the probability that that marble will be red? Well, there's 12 red marbles out of 20 total. Here's our classical probability in play. If we assume that it's equal chance of drawing any of those 20 marbles, there's 12 red out of 20 total, so it's 12 out of 20, or 0.6 when we divide that out, is our probability of drawing out that first marble being red. If I ask what's the probability of the first marble being blue, well, that's 8 out of 20, or it comes out to be 0.4 if we divide it out. So if we're just dealing with a single marble, it's fairly simple. So it's time now to complicate things a little bit. What happens if we're going to draw out 2 marbles? What's the probability of reaching in there and drawing out a red marble followed by another red marble? Now at this point it looks relatively straightforward, but we do not quite yet have enough information to solve this problem. To solve this problem, we need one more very important piece of information. Do we put the first one back? Why is that important? Well, because if we do put the first one back, so yes, we do. When we draw the first marble, there are 12 red ones out of 20. That is a 0.6 chance. If we put it back before we draw the second one, mix them up again to make sure it's random, whatever. When we draw the second marble, there are 12 marbles out of 20. Again, 0.6. So the probability of drawing 2 of them in a row, we'd multiply those probabilities together. That's 144 out of 400, or 0.36. So what if the answer to that question is no, we do not put the first marble back? Well, now when we reach in there, we draw out the first one, there are 12 red out of 20. That doesn't change. Now for the second one, there's only 19 marbles left in the box, so it's going to be out of 19. I always get asked, though, for the second one, how do we know how many red? We don't know whether the first one was red or not. Well, if the first one's not red, if the first one happens to be blue, we're done because there's no way we can get 2 red ones. So we have to assume that the first one was red, or we wouldn't be drawing the second marble. So now there's only 11 red ones left in there out of 19. So this is going to be 132 out of 380, or 0.3474. So you can see that probability is slightly less when we don't put the first marble back. The technical terminology here, and there's a couple of technical terms that's going to come up. This is called with replacement. We put the first marble back before we drew the second one. It was replaced. This is considered independent. Oops, if I can spell it correctly. There we go. Independent. It's independent because the probability of drawing a red marble with the second one does not depend on what we got on the first one. Because we're going to put it back, it doesn't matter what the first marble is. The second marble still has the same chance of being red or blue. This over here, where we did not put the first marble back, you could probably guess, is called without replacement. And this is an example of what we call dependent events. Some textbooks just refer to them as not independent, just a semantic deal. Because here, the chances of getting a red or a blue marble with the second marble do depend on what the first marble is, because you're not going to put it back. So the probabilities will change depending on what that first marble was. So there's what we call conditional probabilities that come into effect because of this. So let's say we want to know, we're going to draw 2 marbles. Still that same 12 red and 8 blue from the box. But I want to know what's the probability that the second marble is red. Don't care what the first one is, we want to know what the probability the second marble is red. Well, we've got a couple of possibilities here. First of all, how many different pairs of marbles can we draw out? Well, the first draw, there's 20 marbles. The second draw, there's only 19 marbles. We're assuming no replacement here, by the way. So the first marble is not put back. If there was replacement, if we did put the first marble back, the probability of the second marble coming out doesn't matter what the first marble is, it's just 12 out of 20. So here, there's 20 times 19, there's 380 possible combinations of marbles that could be drawn out of that box. Now we want to look at how many of those combinations give us red on the second marble. Well, we could either get red on the first one and then red on the second one, or we can get blue on the first one and red on the second one. Let's look at our probabilities here. If the probability of the first one being red is 12 out of 20, times, if the first one's red, the second one would be 11 out of 19. So that is what we had looked at before, our 132 out of 380. If the first one's blue, there is an 8 out of 20 chance of the first one being blue. The first one's blue, then there's a 12 out of 19 chance that the second one is red, because all 12 red ones are still in there, but there is one less total marble. That gives us 96 out of 380. Those two possibilities combine, 132 out of 180 plus 96 out of 180. Okay, so we've got the 132 plus 96, and both of these were out of 380. So that ends up being 228 out of 380. Which is 0.6. There's a 0.6 chance that that second one will be red. Now there are some, I got those right. That looks like it. So anyway, let's take a look at what we call conditional probabilities. I want to know, going back to that same situation, I want to know the probability that the second one is red, but I want to tell you, given that the first is blue. So what that's telling us is we have some information. This probability is what we call conditional. This is the condition. We are assuming that we know the first marble was blue. Based upon that knowledge, what's the probability that the second marble will be red? Well, if the first marble was blue, that means there's still 12 red marbles in there out of 19 that's left, because one has been drawn out. 12 divided by 19, 0.6316. That conditional probability becomes very important when we go to analyze real data. I realize that, okay, marbles in a box is not a terribly realistic, and not terribly useful, at least in the real world data analysis. But if we look at real data, what we call the contingency table that we mentioned briefly before, what a contingency table is comparing two different things to each other. It could be a cause and effect type situation. Could be a lot of different reasons why we would compare two things. But let's take a look here at, for medical fields, let's look at different types of surgeries and whether they were successful or not. So let's look at heart surgery. Let's go brain and lung. Let's do the big ones. And here we're going to have successful and unsuccessful. And let's throw some numbers in here. So let's say that in our heart surgery, we had 148 successful and 52 that were not successful. In our brain surgery, we had 59 that were successful and 41 that were not successful. And for lung surgery, let's say that we have, trying to get my numbers to work out, 129 and 71. So we want to use these now to find some basic probabilities. To use a contingency table for probabilities, the first thing we have to do is we have to find totals. We have to find the totals of the rows. Well, 148 and 52 add up to 200. 59 and 41 add up to 100. And 129 and 71 add up to 200. Which would give us a grand total of 500 here. And we also have to do the total of the columns. So 148 and 59 is 207. 336 there, 93 164, and that also adds up to 500. That's how we can double check. So we have our totals. So what I want to ask now is some probabilities based on these totals. I'm going to shrink it down a little bit so that we can see the whole thing here. I want to know what's the probability that a surgery was successful given that it was a heart surgery. Now here we are not looking at all the surgeries. This condition here tells us that we're narrowing our focus to only heart surgeries. Now, what is the probability that it was successful given a heart surgery? Well, in the heart surgeries, there were 148 successes out of 200 surgeries. That is 0.704. 0.74 is the probability it was successful. Now, not to confuse that with probability that it was heart surgery given that it was successful. So now we're only looking at the successful surgeries. These are the successful surgeries. So we're looking at 336. Out of the 336, 148 were heart surgeries. So we have 148 out of 336. Oops, try it again. 0.4405. So you can see you get very different probabilities there. Remember, this second piece is, so you can see this the second piece here that is telling us how we're limiting what we're looking at. Here, this is telling us we're only looking at heart patients. This is telling us we're only looking at successful surgeries. So it narrows our focus. Well, what if I ask, what is the probability that a randomly selected patient had lung surgery? Now there's no condition. Didn't ask whether it was successful or not. We just asked the probability they had lung surgery. There's 200 that had lung surgery out of 500 total surgeries. So that's just going to be 200 out of 500, or 0.4. Or I could ask, what's the probability that a surgery was successful? Again, I don't care what kind of surgery it was. I just care that it was successful. There were 336 successful surgeries out of 500. Which is, what, 0.372, I believe? Or no, 0.672. I'll double check it. 0.672. So that's our probability of a successful surgery. What we just did here, and you don't need to know this vocabulary, you just need to know how to find it, are what we call marginal probabilities. They're marginal because we're taking numbers from the margins, from the totals. We didn't care about the individual success or failure. We just want to know how many lung surgeries out of the total. We didn't care what type of surgery. We just want to know how many successful out of the total for the second example. Well, we can look at how to combine probabilities here. We can look at what is the probability that a surgery was a brain surgery and it was successful. So here's brain surgery, here's successful. These 59 are the ones that were both brain surgeries and successful. And we haven't limited our population at all, so we're still looking out of all 500 patients. So that is 59 out of 500, which will give us a 0.118, I believe. 0.118 is our probability. So here, because it's an and, it has to meet both conditions. It has to be a brain surgery and successful. So we took the number that was at the intersection of that line and that row and that column, the 59. What if we don't say and? What if we ask, what is the probability that it is a heart surgery, or, I can't bring myself to look at unsuccessful, it's kind of morbid, so we're going to go or successful, heart surgery or successful. So here are the heart surgeries, and here are the ones that were successful. So what we're adding up is these four numbers right here, 148, 152, 59, and 129. Which is 52, sorry, 159 and 129. You need the one out of there, it's just a 52. And this is going to be out of the 500 total. So if we add those all up, we've got 200, 259, 388 out of 500, which is 0.776, I believe. Yep, so 0.776 is that probability. Now there's a shorter way we could have looked at that. When we're dealing with heart or successful, we're doing an or situation. What we could have done was this. We could have looked at this up here and said, hey, this is all of the successful surgeries, 336. This is all of the heart surgeries, 200. If we did 200 plus 336, we get 536. Well, that's more than the 388 that we had. That's not the correct number. Why isn't it correct? Well, because the ones that were both heart surgeries and successful surgeries were counted twice. So we have to subtract out the 148 that were both heart and successful surgeries. If we subtract that out, we are now down to 388 out of 500, which is our 0.776. When we have a situation like that where we're counting two things and it's an or situation, where it can be one or the other, we can just add together the two totals. But we have to make sure that we subtract out any spots where an item could get counted in both categories. If I have, what's the probability that a randomly selected surgery is lung or brain? Am I going to have to subtract anything out here? Well, let's go up to our table. Get my mess out of here. Oops, I'll put my 9 back in there. Successful surgery is lung or brain. So we're looking now at brains and lungs. Is there any spot where those overlap? No, there isn't. So that means we can just take their totals, the 100 and the 200, and add them together. 100 plus 200 out of the 500 total. So that's 300 out of 500 for a 0.6 probability. What is the probability that we have? Okay, I'm going to do it. I hate doing unsuccessful, but it just seems morbid to me. Probability that a random surgery is unsuccessful, or it is lung surgery. So if I look at this, there's my lung surgery, and I'm looking at unsuccessful here. I've got the two totals, 164 and 200, that I can add together. What's going to have to be subtracted out? Well, the spot where they overlap, the 71. So I'm going to add 164 and 200. And I'm going to have to subtract out the 71 where that falls into both categories of being both lung surgeries and unsuccessful out of the 500. So if I add those together and subtract, what do I get? Oh, what is that? 293, I believe, out of 500. So I get 0.586. Is my probability. So you can see these contingency tables are very, very convenient. It allows us to take two things and put them together. Now, if we really wanted to get technical, we could go through and we could use this table to test to see if the success rate is the same for each type of surgery. That would be going into what we talked about as inferential statistics. And I promised you guys we weren't going to get into the inferential side of it. So we're not going to look at how would we test to see if the success rates were the same. There are formal tests. It's called a chi-squared test that we're not going to get into. But just based off of the simple probabilities, we can take a look as well by just converting this contingency table into a relative contingency table. Rather than having raw numbers, we can do it based off of relative frequencies. Now the problem with that is, which total do we divide? Do we take the rows and divide by the row total? Or do we take the columns and divide by the column total? So we have to figure out what is our variable of interest. So let's say we want to ask ourselves, is the success rate independent of what type of surgery it is? So if we're asking that, that means we're focusing on the type of surgery. So we're going to divide by the total here in the rows. So our success rate for heart surgery is 148 out of 200, which is 0.74. For brain surgery is 59 out of 100, 0.59. For lung surgery, 129 out of 100, 0.645. Now you might look at those probabilities and say, you know what, 0.59 and 0.74 are quite a ways away. There is, 15% difference if you converted those into percents. The goal of inferential statistics is to look at that and say, well, with this size of a sample, only 500 total surgeries, what are the chances that we would just randomly select brain surgeries that were not successful, or heart surgeries that were more successful, or whatever? So the bigger this total size is, the more significant those differences in probability are. The smaller the size of that total sample is, the more likely it is that those differences are just because of random sampling, bad sampling, that we randomly selected lung patients that were more successful or brain patients that were less successful. So that is one of the goals of inferential statistics, if you were to go on into a more formal statistics course, is to look at these and say, well, how far apart do they have to be? Or are they far apart, enough far apart now that we can say that there is a difference? Okay, that is basically it for the course. Monday is our test on statistics. And as I said, Wednesday will be your chance to get some extra points back on the dosage calculation. I'll have those, both exams I'll get sent out to you here before I leave today. Things that are going to be on your statistics test that you'll need to know for Monday. You need to know measures of center. In your measure of center, you need to know mean, median, and mode. You need to know measures of spread, which is going to be range and standard deviation. You're going to need to know how to use z-scores to compare two items from different populations. You'll need to know how to use that empirical rule. Or the empirical rule is the bell curve. It's divided up with the mean, standard deviations, and the percents in it. You can either use the percents that I gave you in class, or the book uses slightly different percents. It uses what's called the exact empirical rule or detailed empirical rule. Either one is acceptable. I have both answers on the test. You will need to know how to organize data. Into a frequency table. You may have to know how to make a simple statistical graph, like a pie chart, circle chart, or bar graph or histogram. You'll need to know how to use a frequency table how to find the mean, the median, and the standard deviation off a frequency table. And then you'll need to know all the probability stuff we've been discussing. So in our probability stuff, you'll need to know how to do the probability distribution. Remember, a probability distribution is basically just a relative frequency table. You'll need to know how to do the contingency tables. And then there might be some basic probabilities like the marbles in the box. Know how to figure those out, how to count those and figure those out. Anybody have any questions on what to expect for Monday's test? Okay, well that is it for this week then. You guys have a great weekend and we'll see you all on Monday.